Okay. So today we're going to start with mesh calculus. Okay, it's combinatorial meshes. I use a different heading than the course, just to have some little difference. All right. So meshes traditionally taught us a subdivision of some manifold, but for our purposes, it may be beneficial to look at them a bit more abstractly as some discrete structure that has embedding in a manifold, but the embedding is not that important. The structure is more important. Just like modules or vector spaces, they have dimension, means they have basis of fixed number of vectors, but we're not fixing this basis when we work with vector spaces. Of course, these combinatorial meshes are they're the main ingredient in the mesh calculus that we use for transport phenomena and hopefully for transport of momentum, like elasticity, things like that. And initially, in 2022 paper, I worked only with flat meshes, but then I realized that we can do better, and so we are not limited to flat cells. So first, let's define what a cell is. So first, I'm going to do a definition of embedding, and then do everything combinatorially. So let e be an integer. We say that and x be set maybe some manifold. Some set, let's say set. Anyway, so we say that X usually it has to some topology, but let's ignore that. X is a P cell. If so, there are two cases. The zero-dimensional case may be a little bit more special. So if for P equals 0, X is a single point. Is a single point. And for P bigger than 0, X is I will work in the smooth world in the so I will suppose it's diffeomorphic to P-ball. So this might be open P-ball. Yeah, except get one mark. So this might be open interval, disk, or ball. in general. Okay, so this is a P cell, so it's a point, interval, open disk, so without the bound or open bow, and in higher dimensions as well. So this is 0, 1, 2. Okay. And now let me combine these cells. So let G is integer and M be a smooth D manifold. And I'll go with X this time. It's M in the paper, but I want to use different letters. And M be a set of cells in M. So this is some family of sets in X. Sorry. So it can be said that it's a subset of the Boolean of X. So it can be said that it's a subset of the Boolean of X. More. Concept. Okay. We say that M is a cell complex if so I think one condition we have that maybe regular, it's the right word, regular. If for any cell C in, so there are two conditions. Two conditions. First, if A, B are in M and A doesn't equal to B, then A intersection with B is the empty set. So any two are different. And two, for any A in M, it is the union of its sub. So the closure of M, the closure of A is union of all sets that are less than A. B in M and B is smaller than A. B. So this is this union here. So what does it look like? Let me use 3 colors for a 2D mesh. So we have, for example, it can be so we have things like let me have only 3 points to be interesting mesh. So we have these cells. So we have, let's say, call this 0, 1, 2. This is 0. This is 1. And we have 0, 1, 2, 3. So this is some curved mesh. And we have, for example, this set, the blue one, its closure is the closed this curved triangle. And its union of the three nodes. So here I have non-strict. It's the curve of three nodes, the three edges, and the interior disk. So just so I will use notation N for nodes, E for edges, F for faces, and V for volumes. And so I have that in this case E, V, I don't have volumes here, but this is in general. So in this case, I have F0, its closure, it's N0, N1, N2 with E0, E1, E2, and also F0. And for example, the closure of F1 is N1 with N2, and then E2, E3. This should be curved. So then this is E, and also F1 itself. Okay. So let me do some remark. A regular cell complex. Cells are regular cell complex. If a regular cell complex M induces a partial order. I haven't defined what a partial order is, but a partial order given by subset relation. So we have that. What's partial order? So A is less than A if A is less than B and B is less than C, then A is less than C is included in C, and A, if A is included in B, B is included in A, then A equals B. So if a cell is a subset of another and the other is subset of the first, they're equal. These are the axioms for a partial order. But we will write, so we will write instead A is minorated. A is minorated, something like that, by B. Minorated, or B mom is measured. What's how to call this? Minorated. When I with this sign here, how I call it? Yeah, this is the same here. It's but okay, okay, that A is on the boundary. Okay, A. No, oh, A is a face of B. Let's say this is how we'll call it. Okay. And so now the definition of combinatorial mesh is we start with this some discrete structure and give it an order. So definition. Let M be a partial order. Partially ordered set. We say that so partial ordered set if we have these three relations with we say that M is a combinatorial mesh if there exists as a manifold X and a map embedding let's go, I call it phi from M to P of X such that its image is a regular cell complex. Now let's give example like the before, but a bit more abstractly. So again, so here we start with some discrete set, and we embed it into a manifold. So my result should be like before. So I had some notes here. I call them 0, 1, and 2 maybe. As is the order, I think so. And I had so this was maybe 0, 1, 2, 3, something like that. And this is 0, and this is 1. So I have this as a order. So I have on the top two cells F0 and F1. Then I have E0, E1, E2, E3, E2, E3, and and 0 and 1 and 2. And so I have some order. So F0 has, so this is my this is some discrete set. And F0 has these relations, and F1 has these relations. And then E0 is this here, E1 is 0, 2, so this is this. E2 is 1, 2, and E3 is 1, 2 as well. This is called Digon, maybe Digon, I don't know how it's pronounced, but this is a polygon with only 2 edges. And so we have feel like F0s, these are the blues, these are the reds, and these are the greens. These are the greens, and they're mapped so that this cell here goes here, this point here goes here, and so on. Okay. So we have some just set with some order, and we see that it has some embedding, but not that important what the embedding is. It can be flat edges, it can be embedded in 3 dimension, doesn't matter. And so what is most important is everything is encoded by this structure, and maybe some, like if you give measures to cells, we can use them. But the point is the embedding shouldn't matter at all. So in discrete exterior calculus, for example, they care a lot about the embedding. We want not to care about it. Okay, and here, yeah, so I maybe to finish, so if M is combinatorial, maybe this is notation, not remark. It's a combinatorial mesh. The set of P cells for some, I took the wrong one. The set of P cells, so P is integer, is denoted by MP. I don't know that. Maybe they are different. Sometimes P is used as superscript, but I use subscript. And if D is the maximal dimension, M is the union P from 0 to D. So this is even this is disjunct union. So this symbol is used. P equals 1 to D plus to 0 and P. If there is one maximal, so if there is a maximal D cell, So it contains all other cells. It contains what is a mesh with a single biggest cell? Polytope. We call M, maybe combinatorial. Polytope. So for example, if we removed phase 1 and H1 and H3, we will get only one biggest cell with smaller cells only. Okay. Now, this is the main okay, let's give some examples before continuing. So 0 polytopes are points. No. One polytopes are segments or edges. Two polytopes are polygons, including the Digon, including the Digon. This is the Digon. So this is N0, N1, E0, E1, F0. This is a Digon. It has only two edges. It cannot be made flat. For example, a triangle can be made flat, but the Digon cannot be made flat. And three polytopes, there are more. Three polytopes are tetrahedrons, cubes, prisms in general, etc. Okay.
Yeah, any correspondence with that diagram.
Yeah, you can take a ball and divide it into two spheres. I don't know how it's called, but let's say you have this here. And you take only two volumes, V0, V1. No, it should be, I think it, no, it should be a single volume. And then the upper is F0, let's say F1. And then there are only two edges, E0, E1, and 0 and 1. So the diagonal here is F0, E0, E1, and 0 and 1. And here will be V0, F0, F1, E0, E1, and 0, and 1. And we have all the possible. This is the Digon analog in 3D. I don't know, maybe there exists some name, I'm not sure. I didn't invent the Digon. Okay, important property for all combinatorial meshes that is not. There are many partial orders that don't have that property, but it comes from the embedding, this property. So many properties come from the embedding. So it limits the possible, it limits the class of meshes, the fact that it has embedding. So we have some discrete structure, an order, but then we are limited by the fact that we have to embed it in a certain way. So this is called diamond property. It has a generalization, but we do not need it. So it's diamond property. So P is integer. It can be 0 as well. A is P plus 2 cell. B, C is a P cell. And C is a face of A. Then there exists exactly two P plus 1 cells, B prime and B second, such that B prime and B second, such that A, so C is smaller than B prime and B second, and smaller than A. Why it's called diamond? Because we have A on the top, C on the bottom, and we have exactly two cells, B prime and B second. So it is like a diamond. Here you can see, even for Digons, if you take, for example, V0 and 0, there are exactly two cells. And so for example, in 2D, let me if I take some, so of course for a 1D mesh it's trivial because there are not two cells. So let me D equals 2, a polygon. So we have, or maybe P equals 0. P equals 0. So we have some polygon. And we take, this is the polygon, this is A, and this is C. And they're exactly B prime and B second. Exactly two edges in between the polygon. We can have other cells as well. We can have other cells. But the point is that C is related to this, and we just restrict everything to a polygon. When P equals 1, we have to be in 3D. And let's take a cube, for example. And this is my cells A, this is the volume. And I take some edge here, for example, this edge. I call this A, and the edge is this one, C. And I have two faces here. I have this face, so this is B prime, and this is B second. So there are exactly two faces coming out from this edge inside that volume. Okay. And we have the following theorem, which is how the boundary operator is constructed. So we have, usually it's proven from, what I did? Yeah. It's proven usually from manifolds, but I will not have time. So usually we start with orienting manifolds, and any two adjacent cells have opposite orientations. But so we have the following theorem. So let M be a combinatorial mesh. Then there exists number, so exists so there exist numbers epsilon numbers, epsilon AB in -1, for any pair AB in MP plus 1 MP with B is a hyperface of A. So such relative orientations called relative orientations. Such that we have the following. If we have the diamond diagram, I will just write the diamond diagram. So I have A, B prime, B second, C, C, then epsilon A B prime times epsilon B prime C equals minus in the opposite direction. Epsilon A B second times epsilon B second C. And also for an H, if our H E has nodes n prime and n second, then they are with opposite. Epsilon E n prime is minus epsilon E n second. So for the example I gave before, let's say F0 N0 N1 N2 and then E0. Maybe this was E1, E2, E3. I can fix, for example, epsilon. I will give this as a matrix. So I will call the epsilon matrix. Then I will rename it to delta matrix, which will have. So I have two matrices, epsilon 1. I'll call delta 1 now, which will take edges N0, N1, N2, and give orientations. So N0, epsilon E0 to N0 is, let's say, -1, and then with the other edge should be +1. And then I have epsilon 1 with this, with N0, N2, let it be, doesn't matter. I take it -1 and then 1. It's better to take the opposite orientation, but it doesn't matter for now. Let this be minus epsilon. E2 is in this direction, so like here, like this thing here. So E2 is -1 here, +1 here, and E3 is -1 with N1 and again +1 E2. And then for D2, which is for epsilons between faces and edges, we have F0, F1, and E0, E1, E2, E3. I should spend more time on this, but how the orientations are made. But so yeah, like giving clockwise direction of F0 and see if the edges go on the same face on the boundary. So F0 with H0 is +1 because it goes anti-clockwise, so we give anti-clockwise direction. E2 also is +1, but E1 is in the opposite direction, so it's -1. And here for F1, E3 is in the positive direction, but E2 should go down, but it goes up, so it is +1, -1 here. So these are relative orientations. And to formalize this, let's define the space of chains. So again, start with combinatorial mesh. Combinatorial mesh, D-mesh, let's say. This integer, so the dimension of M. And P is, okay. So we have a D mesh. For P from 0 to D, denote by C, denote CP upper, lower subscript index of M to be the formal space of formal linear combinations, or in other words, the free. It can be any ring, but I choose the real numbers because for physical problems it's beneficial to have some real numbers. Any ring, but I choose the real numbers because for physical problems it's beneficial to have some real numbers. Free over M. So this is the space of formal linear combination. So this is lambda 1 A1 plus lambda, I don't know, NP where let's call this N, doesn't matter. Where lambda E are real numbers and AI are in MP. So we're just adding, we're making from discrete structure, we're making algebraic structure. And if and so we also denote C bullet, so subscript bullet M to be the direct sum. So this is the direct sum from P from 0 to D of C P D. So this is the space of P chains. Space denote the space of P chains. And this is the space of all chains. In M. So this is just a formal sum of the cells in the complex, in the mesh. Now, if we are given a relative orientations, epsilon, define the boundary operator, and we assume that we always have. I mean, they exist, and we just have to fix one. The boundary operator. The curve dp from CPM to CP minus 1M by dp of some cell A to be the sum of all elements on the boundary. So B is set based on element of MP minus 1. And this is epsilon AB times B. So this is a pitch times B. So this is a pitch. Here A is in MP. Now let's make example for here. P minus 1. The result is P minus 1 chain. The input is P chain. So here, so this above picture. D1. I will put some overline here. D1 of, let's say, E0 is the sum of all boundary elements with their relative orientations. So this will be N1 minus N0. So this is a formal combination of cells. D1 of E1 is formal combination of cells. D1 of E1 is N2 minus N0. D1 E2 is, what's this? This is N2 minus N1. And D1 of E3 is again N2 minus N1. And D2 of EF0 is I take the coefficients here. This is E1 minus E1, E0 minus E1 plus E2, E0 minus E1 plus E2. And D2 of F1 is minus E2 plus E3. So we take the boundary elements with their orientations and make a formal sum of them. So the matrices, so we have zeros here. I'll put this in red. 0, 0, 0, 0. So the matrices D1 with and overline and D2 are matrices are equal to D1 in the basis, so it was F E and D2 in F, sorry, this is F E, and here is E N. So these are matrices of boundary operators in basis. In the standard basis of chain. So these are just the coefficients, the matrices. They're defined by the relative orientation. So the relative orientations give the matrices of the boundary operators. And to finish this part, theorem. For a combinatorial mesh, M and P integer, dp plus 1 composed with dp is 0. In matrix terms, dp multiplied by the matrix of d plus 1 is the 0 matrix. This is the 0 matrix. Let's give this here. So, oh.
No, the first one.
Oh.
No, the first one.
Yeah. This is right. Yeah. This is P, and this is P plus 1. And this is from C P plus 1. Maybe C. This should be plus 2. And this plus 1. And this is from CP plus 2m to CP of m. So this is the 0 operator. And here we have P plus 1 and P plus 2 as well. So this is matrix with so it has the rows are P plus 2. So this is in P plus 2 times P. A matrix is and I'll give example for this kind of mesh. Just compute from above, from before, of course. D1 with D2 with D1. So these two matrices. Let's multiply them. So this is D2 is 1, 0, minus 1, 0, 1, minus 1, 0, 1, multiplied with minus 1, minus 1, minus 1, minus 1. Oh, yeah, well, yeah, sorry. Of course. So D2 is 1, 0. Something is. Oh, I'm so disgusted. 0, 1, 1, 1 multiplied by 1, 0, minus 1, 0, 1, minus 1, 0, 1. And this should be 4 times 3. No. 3 times 2, sorry, 3 times 2. But we have minus 1, 1, and then minus 1, minus 1, so this is 0. The second is zeros everywhere. Here we have 1 and then -1. So this is 0. Then have -1 is 1 and then again -1. So this is 0. And the third we have 1 -1 0. -1 plus 1 0. And that is. Okay. And in 3 dimension, the matrices are very big, so don't do that. Okay, I will finish for now. Any questions?